Hello students, yes, I'm on my couch tonight doing the video. My kids are asleep, so it's finally quiet. So here we go. Hope you guys are doing well. I want to take you through linear approximation. This is another key thing in the standard that we need to have at least a basic understanding of. So this is actually in lesson 4.2 in your textbook that you will read. The first half of that lesson deals with linear approximation. The second half deals with something called differentials. I'm not sure how much we're going to dig into that. We'll kind of see how this goes first. But linear approximation is used in differentials to understand that idea. But I first want to make sure you understand linear approximation. So here we go. Linear approximation is also called linearization. Their synonyms mean the same thing. And basically the idea with linear approximation is that you are approximating a curve with a line. So if we have this curve here, if that is our function, that's our f of x function, okay? If we take some a value right here and we find the tangent line to that, at points near A, points on the tangent line are relatively close or approximate points on the f of x function. Okay? So, if we said, well, I'm curious over here at x, what would the y value be of f of x? So, let's say for some reason you couldn't find that. You would do a linear approximation to go along this tangent line using this slope, and you would find this value here, which I lost my squiggles here, that would be approximately equal to f of x. You can see there's a little difference there between what's the actual f of x value and what's the approximate f of x value. But that's what we're doing. We're using this line to find that value. Now, a lot of our answers initially are going to be, they're going to say find the linearization of a certain function at a certain point. So basically, it's, oops, sorry, I got a spinny chair here. We're going to take and we're going to come up with an equation that is L of x. And then this over here is going to be the equation of this line. Okay, so going back to Algebra 1, what's the equation of that line? That's what this is going to be. And then if they want us to approximate the value, in other words, put in an x value, put in some value here that's close to our original one, we will actually substitute that into our equation and get an approximate value. Okay, so that's the idea. Now, let me take you through again. We kind of went through this last video, but if we want to come up with the equation of that line, remember we have these two ordered pairs here. The first ordered pair, sorry, I'm going to sit on my knee. This first ordered pair would be at a comma f of a. Okay, and that second ordered pair would be at x comma f of x. Okay, and so the slope of that line is the derivative there, f prime of a. So if we come here, I think I showed you the other day with slope form, like y2 minus y1 over x2 minus x1, and certainly that works. But the book also mentioned point slope form, so I thought I'd bring this up. So think back to geometry when you first saw this. So y minus the y1, we're gonna just work with this value here, which is f of a, equals the slope f prime of a times x minus the x1 there, a. Okay, so if we solve this, or if we at least get the f of a to the other side, we have y equals f of a plus f prime of a times x minus a. And this right here, if you take out the a and you put in L of x, this is going to be your linearization form. Okay, that's what you need to know. All right, so that's what we're going to be using on all these practice problems now to come up with the linearization. Let me do a quick problem here. We'll do a basic one here, and I'll have you try a couple on this first day, and then I'll give you some more practice after that. So it says use linear approximation of f of x equals x cubed about the point x equals 4 to estimate 4.1 cubed. Now, I have a little bit of beef with spending all this time on linear approximation. I don't feel like I have a deep enough understanding of it to really know why we learn about this, because let's be honest, we could just take 4.1 cubed in our calculator right now. We don't have to estimate it. We could just type it into our calculator. We have the tools to figure that out, okay? But I do believe there are scenarios where this allows us, like the estimation becomes much easier and is just as accurate in situations when you can't actually find the exact value. I'm not smart enough, or I haven't had the exposure to know that and know what that looks like, so I'm sorry about that. I'm just going to show you what the book shows and kind of teach you this process. I wish I felt like I wholeheartedly believed that it was a very important process, but I don't right now. So maybe you guys can see the value and you can inform me of why we need to learn this. So that's your task. See if you can do that. So here we go. If we're going to try and come up with this equation, this linearization for this function at this point, here's what we're going to do. We first need to understand, okay, what is f of, well, let's start out with this. What is a? Okay, so this was dealing with a and f of a and f prime of a. What is a? Well, a is whatever they give you for that value. So in this case, a is 4. Okay, a is 4. And so f of a simply means plug 4 into the function. 4 cubed is 64. Okay. Now what is f prime of a? Well, in order for us to do that, we need to take the derivative of f first. So f of x, the derivative of that would be 3x squared. Okay. So if we plug our a value of 4 into that, we would get 16 times 3, we would get 48. Okay. So we need to understand, we need to find those values first. Hopefully that wasn't too hard. Now it just becomes a matter of plugging it into our linearization function. And we already kind of derived this formula, so no need to necessarily rehash that out. You can just plug in. So f of a is 64 plus f prime of a is 48 times x minus the a value we said was 4. That's our L of x. Okay. Now, usually you can simplify this a little bit, so we'll distribute this through. So we have 48x, and then 48 times 4, what's that going to be? 2 carry the 3, 192. And that's negative 192 plus 64, combining that one and that one. What are we going to be at? If I go 62 less than that, I'll be at negative 130, so negative 128 minus 128, I think, when you simplify that. Send me an email if I got it wrong. So there's our linearization. So if all they ask you for is the linearization, there it is. It's an equation of a line. But they're asking us here to use the linear approximation of this function around that point to estimate what 4.1 is. Okay, so that's saying now plug in 4.1 into this function. You're not plugging it into the original one because that apparently was too hard. So we're going to make it a line, and plugging a value in and calculating the y value for a line is apparently much easier. Okay, so 4.1 in there. Okay, I'm going to grab my calculator and quick do 48 times 4.1. 48 times 4.1 minus 128. These do a 68.8. 68.8 is what that's going to estimate as. Now, I'm curious, if I type in 4.1 cubed, oh, I get 68.921. So I got pretty close. That's the approximation. But there you have it. Okay, so this can be done for any type of function. It can be done with a radical function, a quotient where you have a numerator over denominator, trigonometry, but the same process is followed. Pick out your a, find f of a, find f prime of a, plug it into your linearization, and work from there. It's more algebra, but hopefully the process you won't find too confusing overall. Okay, we'll go with that and talk to you later. Happy Easter.